In this video, we're going to begin taking a look at the need for MPLS VPN. So in traditional MPLS VPN services, the operations of the network are to get traffic from the customer site 1 to customer site 2. Now there are several ways of achieving that transport and getting traffic from the ingress PE to the egress PE. One of those options is BGP tunneling, the MPLS use case. So when we talk about this, one of the things that MPLS was designed to do was to make what they refer to as the BGP free core. So the problem we run into is BGP itself, if we were to enable it everywhere, regardless of the service that we're trying to facilitate, we would run into situations where the global BGP table is large, and we don't want to have that in the service provider core. Now, when I talk about BGP, I'm referring to Internet BGP. So this is going to facilitate internet connectivity for you, regardless of where you might be in the world. So this particular path is one that I don't particularly like to forward into for private WAN connectivity. The irony of this situation is in common BGP deployments for MPLS VPN, the size of the MPLS VPN BGP table is often several times larger than that of the BGP table. And the reason you might be like, okay, well, why is that? Well, the reason for that is because not every customer uses BGP for internet, which isn't a very uncommon operation, and you saw that when we talked about BGP in the for the service provider in the BGP section. But at the same point in time, because it's so much larger, but it's not everybody sees everybody else's routes. The BGP table might be very, very large, but it's very, very segmented, meaning every customer has visibility only into their routes, and so on and so forth. So we could take a fairly large table, maybe 20-30 million routes, and customer A might only have 35 or 40 that he actually needs to be focused on. And that's the beauty of the VPN service. Well, in this particular case here, BGP is still leveraged inside of the MPLS VPN core, and it's needed to be. This is what propagates VPN routes between the provider edge routers. And the ultimate problem we have is IP routing is destination based. So all devices in the transit path must know the destination. And all transit routers must have full BGP feeds. Now, feeds meaning visibility. Not necessarily you must have 400 peers for every particular route. You could have, on average, if you were to go search for bgp.podaroo.net, you would see where this would come into play and see that the caveats that run into it. You might have a router that might have 30 BGP peerings to other providers. Well, that's fine. And you might have 30 different ways to get to the same destination. That's a different situation than what I'm referring to. I'm referring to it in you will have multiple BGP feeds and you'll have full visibility. So if you look at it from the perspective of if you have one BGP peering where you have 600,000 prefixes from one BGP peering, then you add 2 and 3 and 4 and 5, well, you'd simply multiply 600,000 times the number of BGP peerings that you have. You're not going to get a full BGP table from every provider that you're peering with, but you could say the bulk of their peering tables are going to be advertised to you, and that's what you're going to be using to make your best path selection from. With that being said, you could take that to the next level and say, okay, now that I have all these routes, now I have to run the BGP best path selection algorithm, figure out what the best routes are, and then those go into the routing table. So this is where BGP tunneling the MPLS use case over MPLS, it should be actually titled, but this is where the disconnection between the internet and the MPLS capability are brought into play. Now, routing through versus to the core. Now, what this means is transit providers sell transit, not applications. Meaning, if I want to go out and let's say my home internet here is through ISP-A. That could be any internet service provider. I'm not going to be forwarding my traffic to them. I'm going to be forwarding my traffic through them. Meaning, if they have an application or a service that I have purchased and I want to be able to gain access to it, I will point my web browser to a given URL, which is going to be the URL will be the destination that provider, the ASP, the application service provider, is going to be hosting and going to receive my request in for. So if you go to a Yahoo or Google, those are going to be application service providers. I have emails for Yahoo, I have emails for Gmail, I have emails for Rikers Island Training, I have emails for work, I have emails for all kinds of things, and I use different applications for different situations. The application service providers like your Googles, your Facebooks, your Microsoft Azure, your AWS, etc., etc. That's the key difference between routing through means you're just using them to get somewhere else. Getting traffic from one side of the network to the other. Now, traffic routes through the service provider, not to the service provider. So, end client needs to ping end application, not the core link. So, what's one of the things that you would have seen in the OSPF section? We talked about filtering. So, a lot of times, the IGP filtering tends to be one-for-one with the MPLS filtering, which you'll see in the MPLS filtering when we get into LDP and start filtering back the routing table. I don't need a label bound for the transit links between two provider edge routers, or the provider edge router and a provider core router. I don't need that link because you're not routing to the interface of a router that's going to be trying to get you somewhere else. So instead, we want to route to the end station. So ingress PE to egress PE. Now, whether the transport to get us from point A to point B is MPLS, or if we were just floating over the top of the service provider core via BGP, it really depends on the situation, but that's one example. So taking incoming traffic, determining if it is us, if so, route where applicable, if not, move on towards destination that the traffic is being sent towards. So how does this affect core routing? So to the SP core, only the ingress point and egress point matter. So original source and final destination are arbitrary. So there's one way to do this, and this is to tunnel traffic. So simple transit solution is to tunnel traffic over the core from ingress to egress. So I could spin up multiple different ways. So only the ingress and egress devices need to have full end-to-end information, and core only needs to know about the ingress and egress device. This is where the beauty of things like MPLS come into play, where if I want, I could route traffic as it comes in the ingress PE and send it over the service provider to the edge exit egress, all meaning the same thing, the end point that I'm trying to reach, which is going to be the egress PE, and I want to forward that. I'm going to continually refer to the PE here, and the reason I refer to it as the PE, or the provider edge, is irrelevant of the transport between the ingress and egress PE. Okay, so that could be MPLS, it could be IP, it really makes no difference whatsoever. So how can we tunnel? We could tunnel Q and Q, GRE, IP and IP, MPLS, etc., etc. MPLS is the de facto standard, and you'll see us take a look at a lot of MPLS, but we're also going to be taking a look at IP-based tunneling, layer 2 tunneling, etc., like that. So when we get into layer 2 VPN, you'll see us work with Q and Q. When we're doing over the internet, we'll do GRE-based L3 VPN, etc., etc., and we'll see exactly how that comes into play. Now, BGP over GRE over the core. So from a BGP peering on the edge to the customer site, so you're going to form a PE to CE connection from the customer to the provider. And then once you've hit the provider, you're going to form a GRE tunnel from the ingress PE to the egress PE. And you're going to have a subnet that sits on that GRE tunnel. What you're going to do then is you're going to peer BGP from ingress to egress router using that particular link as your connection to the remote end. But instead of using the tunnel interfaces, tunnel 1 and tunnel 1, 10.0.0.1 and 10.0.0.2, as long as both routers see each other's loopbacks and can reach them, that's where you're going to form your iBGP peering. Just like you would normally in regular iBGP, but instead of you doing it over any arbitrary connection, you're going to be doing it over a GRE tunnel. And then you're going to recurse BGP next hop to the tunnel. So you're going to say, you know what, if I want to get to there, I need to go ahead and specify the next hop. So you would specify a route map that tells you to the local IP is out tunnel 1, and to go from there. So what does the core's data plane result in? So the core routes ingress PE to egress PE, and the core does not need end-to-end information. So the problem with this, though, the big problem, is this is a static configuration. Now, I did have a discussion with a gentleman not too long ago regarding trying to leverage the ability to not use MPLS in the core, but rather use a DMBPN style solution. His argument, and I'll go off on just a tangent just for a moment here, because his argument did have some validity, and so I wanted to hear him out, where you have a route reflector as the hub, and you end up taking, and regardless of the provider, you're going to need BGP, so it would be iBGP peerings. So you would end up taking a route reflector or two, and you would set up DMBPN, and you would run iBGP with dynamic neighbors on the hubs, and then you would set up connectivity between all of the PE routers, the egress and ingress PE routers. So two provider core routers would be your hub, or your hubs, I should say, and your PE routers would be your spokes. And then you would set it up to where you could spin up on-demand GRE tunnels between the provider edge routers. Now, typically speaking, GRE tunneling is tied with IPsec. In this case here, you wouldn't need that because of the fact that it's just private WAN anyway. I let him run with it, and I've never tested it, but I can see how it could work. It could be a solution to get everything up and running. However, I don't know if I would go with... the one thing that I pointed out in the conversation was the more overhead you have, even if you're using MPLS as VPN transport between the provider edge routers, you could remove the MPLS aspect of it and just use GRE to get communication between them, because it's just encapsulation. All MPLS is encapsulation. It's and the encapsulation in this term here is injecting a label in front of the IP header, and you're forwarding via the transport label from the provider edge, the incoming provider edge router to the egress provider edge router. It's an interesting use case. I don't think that I've never seen any provider use that solution, but that's just more or less taking something in the enterprise that you're familiar with and throwing it into the service provider core. It's one of those things where there might be 100 different ways to solve something, and that might be a less common way of doing things. So where does MPLS fit into the picture here? So MPLS is the core's tunnel encapsulation. So same exact logic as GRE, except for the fact now that it's much, much more flexible. So here's a key factor here. I don't care what the transport is, I don't care what the payload is, and I have extensible applications. So instead of me trying to form a BGP peering over a GRE tunnel, I can use BGP over MPLS over the core. So you form MPLS tunnels from ingress to egress. So normally what you're going to do, and in our first couple of videos here, we're going to, and as we get through LDP, we're going to be taking a look at setting up IGP and LDP to get communication where we're going to go. And I want to be pretty specific here. Then when we talk about LDP, we're referring to it as the transport label. Now we're going to talk about MPLS in more detail as we go along and do a bunch of Wireshark captures and understand the flows. But the key factor here that I want everybody to understand is that when you're dealing with LDP and BGP allocation of labels, and RSVP with MPLS traffic engineering, or segment routing, or MPLS transport profile, or whatever mechanism we're using, all of these techniques are regarding the transport label. Okay, this is the key factor that I want you guys to remember. This is not the VPN label, which is allocated by VPN v4. So we're going to talk about the differences as we go forward, but that's the idea here. We're going to be leveraging multiple different options as we go through the service provider course on how multiple aspects of the configuration can be used. So we could throw LDP and have LDP set at the transport label, and then BGP VPN v4 can allocate the VPN label, and then we could be routing over a TE tunnel. And then if we need to, we could have more advanced configuration where we're doing fast reroute and other advanced topics, and carrier supporting carrier and stuff like that. We're going to be taking a look at a lot of really interesting use cases, looking at how the technology works from the ground up and exactly what it is that really needs to be understood, because that's going to be the key factor here. I think is going to be what are the different ways you could solve the same solution, and see and go about it that way. Now, to flip over from BGP over GRE over the core to MPLS over the core is on the edge routers. Set the route map to the next hop to the local /32 loopback, and if using OSPF or ISIS as the routing protocol, you would specify the MPLS LDP autoconfig, which turns on MPLS on any interface running IGP already. And if you're not running IGP or OSPF or EIG or ISIS, which is completely supported, you can run this with RIP or EIGRP, or so pick your protocol. You would specify MPLS IP on all interfaces to run MPLS. Now, to actually get this up and running, you would then peer BGP VPN v4 from the ingress router to the egress router, and then you would recurse BGP next hop to the MPLS label. So the core's data plane now is core label switch traffic between the PE, the egress PE, and the ingress, or I'm sorry, the ingress PE and the egress PE, and this is known as the transport label, and it's used to reach the egress PE. The core does not need to know end-to-end information and will not see anything from the customer, because the customer routes are actually in a different routing table. So you have the global routing table that the provider routing is sitting inside of, and then on the provider edge routers you create VRFs for all of your customers. That's why we talked about VRFs in the previous video, so that we would understand how this particular logic would come into play, so that we can go through and get the core configuration up and running, and then we can go and in a couple of videos from now we'll go through and get the VPN v4 up and running, and we'll take a look at all the details, because as it sits right now, until we actually get to the point where we've covered all the LDP options for just setting up core LDP forwarding with authentication and filtering, etc., then we'll be able to get VPN v4 up and running in a full mesh and a route reflected design. Once we have that piece in place, we'll be able to take it to the next level and actually get the PE to CE routing working, because as we go through, it's going to be important to see how transit traffic works and how that comes into play. Now, from a recursion perspective, the transport label is used by the SP core for ingress to egress PE traffic. So the VPN label is assigned by VPN v4 and does not get modified, and relies on the transport label to reach the egress PE router. And that's going to be the key factor here, is the transport label gets you from the ingress PE to the egress PE. The VPN v4 label is what they refer to as the inner label. The transport label is what they refer to the outer label. The outer label is what gets modified on a per hop basis. Although what's kind of interesting about the whole situation is it may look like the transport label doesn't change on a per hop basis, when I can assure you it does. Now, what's actually kind of funny about this was, going back probably 3 or 4 years ago, there was a training video that one of the large training providers had produced, and the instructor had made a comment about how, and this is applicable to the route switch track, but it could be applicable to the service provider track as well, where depending on the level of detail that they want you to go into on the forwarding aspect of things. For the route switch folks out there, when it comes to MPLS, you're not really going to be required to manipulate the label values that you're seeing. What you're going to be seeing is the transport labels that are going to show up might differ from the transport labels that you see in the outputs for verification. And if that happens, that's fine. However, as you get more familiar with MPLS and label forwarding, you will find that you can, if you want to, depending on the size of the SP core, you could configure MPLS in such a way to guarantee that every label that you see in the verification actually shows up as that label. It's called static labeling. And you can go on a per hop basis and set up static labeling between a group of PE and provider core routers to show the label values that you need to see. We're going to talk about that down the road when we get into some of the more of the advanced options for MPLS. So a lot of the LDP aspect of things we're going to be hitting. More of the advanced things like traffic engineering and segment routing, MPLS transport profile, inter-AS VPN, layer 2 VPN, carrier supporting carrier. There's going to be a significant dive into the MPLS. You're going to see that aspect of things geared towards service provider. So we're going to take a generic look at TE and route switch, but at the same point in time, we're going to be taking a much deeper dive into the aspects of it for service provider. So stay tuned for that. That's going to be basically how I would queue it up for you to set the expectations of what you're going to see. But until next time, guys, thank you so much for stopping by, and we'll catch you guys in the next video.